Welcome to my workshop in the second installment into the BJT Curve Tracer series of labs. When complete, your BJT Curve Tracer will generate the characteristic family of curves for a BJT, similar to the one I have shown on the oscilloscope here. This week, you'll be building a Schmitt Trigger Relaxation Oscillator. This circuit will generate a square wave similar to the one you generated last week using a different circuit. How does it work? Great question. Let's go to the whiteboard. Here's the essential circuitry for the Schmitt Trigger Relaxation Oscillator. As you can see, it utilizes an op-amp, which will be part of the TLC-274. You'll solder in the socket and populate the IC into that socket. A variety of resistors, diodes, one-way valves for current, and a capacitor, 100 nanofarads or 0.1 microfarads. Let's explain how the circuit works. When initially powered on, the voltage on this capacitor is 0 volts. Meaning the inverting input is 0 volts. This voltage divider on the left side here will ensure the non-inverting input is larger than 0 volts. That difference will cause the output of the op-amp to increase. Since there's a capacitor on the inverting input circuitry, the output on the non-inverting input will rise much more quickly. And that will ensure that Vout goes to 9 volts. Now, there are two things you need to track in order to understand what happens next. What happens on the non-inverting input and what happens on the inverting input. Let's look at the non-inverting input. If this node is at 9 volts, this 10K resistor is in parallel with this 10K resistor. Both have their high side at 9 volts. Two resistors in parallel, two identical resistors in parallel will half the resistance. So there'll be effectively a 5K here and a 10K here, causing the non-inverting input to go to 6 volts when Vout is 9 volts. So this is stable at 6 volts. The inverting input will have its voltage increasing because this 9 volts can send current to the upper plate of that capacitor through the upper diode here. That accumulating positive charge, the time constant of which is the 100 nanofarad and the 1K, will steadily increase the inverting input's voltage until it gets above 6 volts. Let's see what happens then. When the inverting input voltage goes above 6 volts, look at this op-amp. We have 6 volts on the non-inverting and something larger than 6 volts on the inverting. Therefore, the voltage output will tend to decrease. As soon as Vout starts decreasing, this voltage will decrease faster than the inverting input because there's a capacitor on the loop. This will cause Vout to drop to 0 volts very quickly. There are two things you need in order to understand what happens next when Vout is 0 volts. What happens on the non-inverting and the inverting. When we have 0 volts on Vout, this 10K is now in parallel with that lower 10K, effectively making a 5K resistor. And this Ohm's law dictates that the non-inverting input will be fixed at 3 volts. What will happen now to this capacitor on the inverting input? Well, those positive charges that we accumulated during the 9 volt phase will have a path to 0 volts through this lower resistor here, 100K. The time constant of that decay will be 100 nanofarads, and dictated by the 100 nanofarads and the 100K. That discharge will be slower than the charge, meaning the circuit will spend more time at a logic 0. This discharge will continue until the inverting input goes below 3 volts. When that happens, the non-inverting is greater than the inverting. The output of the op-amp will increase. That increase will be faster on the non-inverting input because there's no capacitor in that path than it is on the inverting because there's a capacitor in that path. And what will happen is the charging sequence will begin again, charging and discharging. Let's see what that looks like under the oscilloscope. You can see the output of the Schmitt Trigger Relaxation Oscillator on the oscilloscope. If you've been asking yourself, why don't we just use a 555 timer, you're correct in theory that this would work, but in practice I wanted you to learn some new concepts this week, so we're using a different oscillator. Assembly-wise, you'll be assembling the circuit in this upper corner here as well as the socket for the TLC-274. Now that you understand the theory of what you need to accomplish, let's talk about the specific deliverables for this week's lab. The theory, you'll look at the charge and discharge time of the circuit. And remember, that's a result of the 1K and 100K and the 0.1 microfarad capacitor. You'll then simulate the circuit using LT-SPICE and compare your results against those predicted by the theory. You'll then assemble your circuit and probe the capacitor and output pins of the TLC-274 to check and compare against your simulations and your theory. You're going to perform some tests, and turning in, you're going to put the results of your analysis, simulation, and assembled circuit in a table 4, as well as features of the capacitor voltage, which are indicated in the figure below. You'll save all of these as a PDF. You're welcome to work in teams of 2 to submit a single PDF, but each student is responsible for assembling their own circuit board. Thanks much. Good luck and good hunting on this week's lab.